Okay, we're back here, and now we're going to talk about thermodynamic processes and also, state of a given system, thermodynamic system. Okay, in this section, we will talk about thermodynamic processes, different processes, different thermodynamic processes. Let's talk about different thermodynamic processes and thermodynamic states. The first thing you have to know is thermodynamic states. What is a thermodynamic state? What is a thermodynamic state? Okay, a thermodynamic state, defines basically the energy state of a system. And there are thermodynamics variables. Okay, a thermodynamic state carries information about the energy of the system. Within a thermodynamic state, we have what we call the thermodynamic variables. What are those thermodynamic variables? What are the thermodynamic variables? Okay, pressure is one of them. Just remember the ideal gas law, right? Pressure is part of that ideal gas law. Volume is a thermodynamic variable. It affects the energy of the system. So does pressure. Temperature, the number of moles of a gas, number of moles of a substance. And the internal energy. Those are all thermodynamic variables. Take a look here. What I call thermodynamic variables, the book calls it state variables. Pressure, temperature, volume, number of moles, and internal energy. So those are all, we already defined internal energy, right? Which is basically is the potential energy of the system. That's what internal energy is energy that has the potential to do work, to do useful work. That's what the internal energy of the gas is all about. So 1, 2, 3, 4, 5 different thermodynamic variables. 5 different state variables. At a given pressure, a given volume, a given temperature, with a given number of moles of a substance, and with a given internal energy, we say that a system has a given state. Is not has a given state, but is in a given state. Okay. Now let's talk about the thermodynamic process. What is the thermodynamic process? Thermodynamic process is a process through which a system changes from one state to another. Change from one energy to another energy value. And there are, some interesting thermodynamic processes that we're going to study right now. It's not difficult to understand that, and there is a very useful way to understand it better. Okay. So one very useful way of understanding a thermodynamic process is by analyzing what we call the PV diagram. What PV stands for? PV diagram stands for, the pressure versus volume diagram. Pressure versus volume means what? Pressure in the vertical axis and volume in the horizontal axis. This PV diagram not only helps you visualize different states of a system, of a gas, for instance, but it also helps you visualize the work done on a gas. So that's how important the PV diagram is. Okay? This diagram, here, let's write it down. This diagram helps you visualize not only the different states of a gas, but also is a useful tool to determine the work done on a gas / system. Don't forget, every time that I'm talking about gas, I'm actually referring to a system, right? System is a more generic term. Gas is just one specific type of system. We're going to investigate this diagram right now, and you need to get good at that. You need to understand that, and you need to know how to find out the work done on a gas by using that diagram. But however, before we look at this diagram, let us see how we can calculate the work done on a system. Okay, let's see how we can calculate the work done on a system. I have already told you before that, if a gas expands, the work done by the gas is positive. In other words, the work done on the gas is negative. We discussed that before, right? However, if the gas contracts, the work done by the gas is negative, whereas the work done on the gas is positive. Gas expand, and the work done on the gas is negative, but the work done by the gas is positive. Gas contract, the work done on the gas is positive. The work done by the gas is negative. This is just a qualitative way of seeing that, but there is a quantitative way of calculating that. What we did before, and is stated above, is just a qualitative way of determining the work on a gas. What we will do in this section is to show you how to determine the work done on a gas in a more quantitative fashion. Okay? Quantitative quantitative fashion. By calculating the work done on a gas, we may get to the point of finding the changing internal energy of the gas. Remember, first law of thermodynamics, right? If you want to know the change in internal energy of a given gas, you have to know at least the work done on the gas, and you also have to know the heat applied or extracted to the gas from the gas, applied to or extracted from the gas. So let's see how we can calculate the work done on the gas, and then we move on to the PV diagram, right? The PV diagram will allow us to calculate the work on the gas. But first, we have to know how to calculate the work on the gas. Here we go. The first step in calculating the work, remember what is the definition of work, right? Here we go. Definition of work is force times distance. That's the generic definition that you saw there in physics 120. Here you go. Force times delta x. So try to visualize that. We are not talking here. Here is the definition of the work by the system, right? The work done by the system is always convenient. First, calculate the work done by the system. It's easier to calculate the work done by the system. And then you just take the negative here of this value to find out the work done on the system. Go. Like that. On. Like that. So we have to visualize a gas in a cylinder and a piston. That's the best way of, here you go. Here piston, cross-sectional area A, and the gas is initially at this initial state. The cylinder is the best way, the easiest way to visualize this process. You don't want a conical, a conical tube. No. The mass becomes too complicated. Okay, you want a cylindrical tube, so you have an easier way of calculating the work done by the gas. So the cylinder is initially at this initial volume, initial pressure. That's the initial state, initial volume, initial pressure, initial temperature. Initial number of moles, in this case the number of moles doesn't change, initial internal energy. And then in this case the gas is expanding. Okay? Qualitatively speaking, you already know that the work done by the gas is positive and the work done on the gas consequently ends up being negative. Okay, so how do we calculate the work done by the gas? Okay, if this gas is expanding, this gas is applying a force here to this piston. Okay, and the distance that the piston travels is d. So let's use the notation of the book. Instead of delta x that I use here, let's use d. That's the force that the gas is applying to the piston and is expanding in the process. Okay, let's assume that this force may vary along the way. Okay, this force may vary along the way. So let's go ahead, and that is, remember, there is a relationship between the force and the pressure, remember? Here you go. The pressure is what? Is force divided by the area. Consequently, what you end up having is that the force can be rewritten as the pressure times the area. Okay? We substitute this relationship right in here, this formula. And we get a very simple relation, A times D is that what we call the delta V. How much volume change, how much change of volume we got. The delta V can be positive, the delta V can be negative. So that's the equation that you have to know. Do you see that? We can relate the work done on the gas by those two state variables, pressure and volume. Since you are interested only on the work done on the gas, we're going to rewrite this equation as being minus P times delta V. And now we are going to apply this relation to the PV diagram. Here you go. Here's the PV diagram. Well, this one is a little bit complicated. I wouldn't introduce this one as the first one to you yet. Okay, I don't see it. Let's do one of the simplest type of processes, one of the simplest type of thermodynamic processes that a gas go from. Okay, so here you go. Let me show you. We are going to look at the following thermodynamic processes. Okay, the first one, process at constant volume. And we're going to visualize that in the diagram. That's the simplest of one that you're going to see. Constant process, a given process at constant volume. Volume doesn't change. What happens to the work done on the graph, on the gas, on the system? Another one at constant pressure. There is another process at constant temperature. At least three processes. There one more, at least one more. Let's take a look. Go. Constant pressure, constant volume. Did I say constant temperature? Yeah, I said constant temperature. And there is what we call adiabatic process. Okay? Adiabatic process. Those three are easy to understand, right? They're kind of obvious. Then I'll have to define to you what adiabatic. Oh, I'm going to tell you right now what a adiabatic process is. A adiabatic process is one in which there is no exchange of heat. No heat is introduced to the system. No heat is extracted from the system. That's the definition of a adiabatic process. Can you memorize that? So let's take a look at the simplest of all processes that we can have in a system. Constant pressure, constant volume. What is the work done on a graph that undergoes a constant volume process? Let's take a look here. That's the easiest one, okay? That's why I want to introduce you to this one. Here you go. Just go back to your equation right in here. When the volume is constant, for constant volume, final volume is equal to initial volume. which implies that delta V is equal to 0. Make sense? Simple enough? Like I said, this is the simplest process that you're going to see out there. The simplest one that will allow you to calculate the work done on a gas. Symbol. Here you go. Here you go. Vf equal to V initial. That implies for a thermodynamic process with constant volume, that implies that the work done on the gas is equal to 0. Simple enough. Which means that according to the first law of thermodynamics, the change in internal energy or potential energy is going to be equal just to the heat introduced or extracted from the system. Okay, so if you know the heat, you know what was going to be the change in internal energy of the system. That's the simplest one. In the PV diagram, how does it look like in the PV diagram? I'm going to get my PV diagram here for you. In a PV diagram, the process looks just like that. Constant volume, we also call it isovolumetric process. You started at the initial pressure, let's say, at a given volume, and end at a final pressure. This is one state of the PV diagram, one state of the gas. This is another state of the gas. To visualize the work done by the system, what you have to do, you have to calculate the area below this graph. Okay? There's no area whatsoever. The area is 0, right? Because the process is done in an isovolumetric fashion. So this area that you see here is exactly 0. Whether you go upwards or downwards, the work done on the system is still going to be 0. That's how you visualize that in your PV diagram. Pressure in Pascal, volume in cubic meters. Simple enough. Okay? So in the next one, constant volume, I'm going to put that isovolumetric. Volumetric. Then you have another process. The second easiest one to calculate is the constant pressure. Isobaric. Isobaric. For constant pressure. Now, P final is equal to P initial. Okay? I would say delta P is 0, right? But we don't need to write that down, delta P is 0. And now it's just a matter of calculating what's going to be the work done on the system under constant pressure. Here you go. Simple enough. This value doesn't change, but this value here changes. So all you have to do is to write down like that. Here you go. Delta V means what? Delta V means final minus initial. That's what delta V means. Let me get that. V final minus V initial. Simple enough, right? So here you go. Depending on how the volume changes, the work on the gas is going to be either positive or negative, and the change in potential energy or internal energy. Don't forget, it's a change, it's not the actual value of the internal energy, right? It's a change in internal energy from one state to another. It's going to be given by this equation here. Isobaric. How do we visualize that in a PV diagram? That's easy. Going back here. Here you go. Here you go. The pressure doesn't change. You go from initial volume to a final volume. Remember that I told you the work done by the system is going to be the area of this curve here. The area of this graph under the curve. If it's moving from left to the right, the work done by the graph is positive. The work done on the gas is going to be negative. Right in here. For isobatic process. If the volume changes, if the initial volume is larger than the final volume, then the work done on the system is positive. What happened? Yeah, the work done on the system is positive. The work done by the system is negative. Those are the two simplest ones that we have. It's very straightforward to calculate the work done on the system. Okay, things start to become complicated when we have a constant temperature. Mathematically complicated. Okay, so here you go. Constant temperature. Isothermal. During an isothermal process, final temperature is equal to initial temperature. For constant temperature, okay, let's first look at how it looks in the PV diagram, right? But let's see here. Before you do that, let me show you in the book, right? Constant pressure process, right in here. See the negative sign, right? And now let's look at the constant temperature process. Constant temperature process looks somewhat like that. It's not difficult to understand why it looks like that, okay? It's not difficult to understand. Specifically for an ideal gas, the pressure is inversely proportional to the volume. Specifically for an ideal gas, okay? So let's go back here. For constant pressure, Tf is equal to Ti. Okay? So let's visualize how that happens specifically for an ideal gas. We have the following relation between the state variables. Here you go. P, right? An ideal gas, the ideal gas law, nRT over V, right? That's how it looks like. So if you're going to plot something that in a PV diagram, it's going to behave exactly the way it's shown here in your book. That is one isotherm, a temperature T2. That is another isotherm. Isotherm means constant temperature, a temperature T1. If the gas is compressing, it's going from this initial state to this final state. And the work done on the graph is going to be this area here. To calculate this area, it requires calculus, okay? To find out the area below this curve, you need to have calculus, but we're not going to do calculus here. But at least you have to understand that how you visualize this isothermal process in the PV diagram. I have that in my, here you go, looks like that. You start, in my case, you start at the initial pressure and goes to a final pressure, initial volume, final volume. And the process follows an isothermal curve. So if you want to memorize, here you go. The result of the work done on the graph is this formula that you see here. We will be taking this formula from calculus. Okay? That's here you go. We have work done on the graph is positive in this case. Work done by the graph is positive, right? Work done on the graph is negative for this one here. For this case here, the work done by the system is negative and the work done on the system is positive. So going uphill and going downhill. Here you go. Okay. When we calculate, so how do you find that out? Here you go. We have this situation here, right? The work done on the graph is pressure and volume. It's varying. Both of those variables are varying, are changing. So it's not a straightforward calculation. It requires calculus. If I substitute my P right in here, and I take into account that V is delta V is very small, we can integrate. We can use calculus, okay? We can use calculus to determine the work done on the gas, which ends up being something like that. nRT, right? When you take the integral of the inverse of V with respect to V, we get this log function. If V naught is greater than Vf, the log is positive. If V naught is less than Vf, then the log is negative. So let's see how he did in the book. Here you go. Constant process. Here you go. So how do we do that without calculus? How we do that without calculus? Well, we divide this area in very small, into several small trapezoids. Okay? Trapezes. Okay? And then you sum the area of each one. You know how to calculate the area of the trapeze, right? You sum each one, and you get an equation just like I put in there. Here you go. Finally, we have a adiabatic process that I already told to you. Oh, let's see. We gotta put one more equation here, right? Delta U here in this case is going to be Q plus nRT for an ideal gas. We use calculus. On an ideal, okay, here you go. On an ideal gas, we will obtain the following. Obtain the following. What you see here is also an ideal gas. But even if the gas is not ideal, even if the gas is not ideal, the curve is slightly, it's just slightly different from that. Just slightly different, okay? The isotherm, let's write that down. The isotherm curves of a non-ideal gas is slightly different from that of an ideal gas. And then finally we have adiabatic process. Adiabatic process. By definition, just remember that an adiabatical process by definition is a process in which there is no exchange of heat whatsoever between the system and its surrounding environments. And the change in internal energy becomes just equal to the amount of heat that is input or subtract from the system. Hey, wait a minute. No, it's all the way around, right? Yes, here you go. Right in here. It's like that. Just equal to the work done, because Q is equal to 0. Let's take a look at your illustration here. Here you go. Adiabatic process. Let's see if they have one. They don't have it. But unlike adiabatic process, looks somewhat. Let me see if I have an illustration here for you. I don't have an illustration here, unfortunately. Yeah, let's see, is this one here? No. But another adiabatic process looks somewhat like the following. I'm going to show you here in this graph. An adiabatic process is something that goes from here to here. Somewhat, alright? You have a change in pressure, a change in volume, a change in temperature. Okay? That's what you have to know. Those are the important processes that you have to know, that you can use to find out how to calculate the work done on the system and the change in internal energy. We have a little table here that summarizes everything that we did. In the next session, we are going to talk about thermodynamic process for an ideal gas, like you're saying here, so we can get more the specific results, numeric results. Okay, so see you next time.